Hello everyone, welcome to another PrismSPECT video. Here, we will go through a simulation example where it is more advanced than those shown in the introductory video. A common diagnostic for short pulse laser experiments is the cold K-alpha, K-beta emission resulting from transitions in the inner shell of an atom or ion. Such inner shell transitions occur after the ejection of K-shell electrons by interactions with energetic electrons or photons. In this example, we simulate the cold K-shell emission from a copper foil containing hot electrons. This is motivated by experiments by the Omega EP laser with 100 joule 1 picosecond pulses at focus intensities above 10 to the 18 watts per square centimeter. In this simulation, we will not be looking at the K-beta, we will focus on the K-alpha-1 and the K-alpha-2 emission. To set up the simulation, we will first add copper from the periodic table. For the atomic model, let's have a look at the default model called Emission Visible UV-EUV Spectroscopy. The View button should launch the Atomic Model Builder application. If you are using Linux or Mac and the button does not work, you may need to set up the path to Atomic Model Builder in Preferences. Here, you can see that we are including some atomic levels from the lower ionization stages. This default model will be sufficient to show the general effects of ionization on the K-alpha features. However, a properly quantitative treatment may require a more detailed custom atomic model. A full look at using Atomic Model Builder will be done in a future video. For now, we will stick with this default model. To mimic the evolution of the signal over the course of a laser pulse, we will do a time-dependent simulation. For our copper foil, we choose planar geometry. The electron distribution dropdown is where we can choose to include hot electrons. The hot electron distribution can be defined either by another Maxwellian distribution, an analytic expression, or a histogram distribution. We will use dual Maxwellian. And we will specify them by a fraction of the thermal electron. We will leave the density as defined as mass density, and the size defined as delta L. Here, in this table, we can define the simulation times. Let's delete 0 with edit, remove rows, because we will be using a log scale for the first part. We can fill the table using the Add Points to X Grid button. Some care should be taken in setting these time steps. In a time-dependent non-LTE simulation, populations are initialized to LTE, so we should use a relatively dense timing grid in order to reach a good calculation of non-LTE populations at the beginning. So, logarithmic spacing for 50 points from 10 to the negative 16th to 10 to the negative 12 seconds. After a good approximation for non-LTE has been reached, we can give it linear spacing with a coarser gridding. Let's add another set of 100 points with linear spacing from 10 to the negative 12th to 10 to the negative 11th. Hitting the sort button will remove the redundant entry of 10 to the negative 12th seconds. We can create a temperature change by choosing variable and entering some table values for temperature. Let's simply add points at the beginning and end of the simulation, 10 to the negative 16th and 10 to the negative 11th, beginning at 1 eV and ending at 350 eV. The temperature at each time will be extrapolated linearly. This is an oversimplification of the temperature rise during a laser pulse. You could also set up a more complex temperature profile in this table. Let's use a constant density of 8.96 grams per cubic centimeter for copper solid density and a foil thickness of 2 microns. And here we can choose the hot electron fraction of 0.001 and a temperature of 200,000 eV to define the Maxwellian energy distribution for the hot electrons. In order to simulate the cold K-shell emission, we cannot assume LTE populations. Choose non-LTE and go into Advanced Settings. In the Transitions tab, select the box to add K-alpha and K-beta transitions. Let's include those transitions for ions down to 11 bound electrons. This is necessary because relevant levels may not be explicitly included in the calculation. We use a semi-empirical model to account for inner shell transitions. We expect the emission features between 8 and 8.15 keV, so let's give that range to the photon energy grid. Let's keep 200 continuum points and 13 additional points per transition. Let's run the simulation. This one will take some time due to the size of our atomic model. This took about 30 minutes, multi-threading on a machine with 16 cores. Let's take a look at the results. For time-dependent simulations, the strict spectrum option will be available. Using the Shift key, let's select all the time steps. This 2D plot shows the emission spectrum of the plasma each time in the simulation. Looking at the initial time at the bottom of the plot, we can see the two characteristic K-alpha lines when the copper plasma is still cold. As the plasma heats up over time, the resulting ionization leads to a shifting and broadening of the features. This is due to K-alpha contribution from higher ionization levels where electron screening effects are altered. Let's bring up a plot of the ionization alongside this. In this list, we can see the population of each copper ionization level at the time given in this drop-down menu here. At our initial temperature of 1 eV, PrismSPECT is giving essentially zero population to the first 3 ionization stages. This is due to pressure ionization of the outermost electrons for this solid density copper. So let's make a plot versus time of the level of this for copper 4, which is the lowest ionization stage populated at these conditions. We can see that the relative population of this ion drops quickly as the plasma heats up. Let's put it on a log scale. We can bring up a few other ions on the same plot using the Control key or Command on Mac and clicking the arrow button again. The higher the ionization, the later in time it becomes prevalent in the plasma. Higher ionization levels result in a higher blue shift in the K-alpha emission, and contributions from multiple ionization levels add up to produce broad and multi-peak emission spectra. By comparison with simulations like this, characteristics of an experimental plasma and the hot electrons produced by a short pulse laser can be understood. This concludes this PrismSPECT video example of the time-dependent cold K-shell emission from a non-LTE copper foil containing hot electrons. Thank you for watching.